our nation, our country is passing through critical times. Second wave has hit us badly, and even in the national capital region, we are affected. But there is a silver lining. The last about week to 10 days, there has been a marginal improvement. And if we consider them as a positive trend, maybe another week to 10 days' time, we should see the situation improving. But till then, our humble request to all of you and through you, all those who are connected with you, stay safe, stay healthy, stay home. Okay, having said that, it's my privilege once again to reintroduce our organization, that is the Tunneling Association of India. I know all of you are aware by now, but then every time, like a broken record, I must speak about it. Now, you are aware that the Tunneling Association of India is under the aegis of the Central Board of Irrigation and Power. That is our umbrella organization. We joined the International Tunneling Association, that is the ITA, in the year 1976. We are the official representatives of India as a member nation. We have more than 600 members, individual members, institutional members, and we encourage more and more people to join us so that we are a large forum where more and more people can exchange ideas and gain. We are aware that for all matters which are dealing with the underground space, we are the single agency which is the repository of knowledge, experience, and also the standards. We conduct training like this one. We conduct seminars. We conduct annual events, including as and when the ITA would give us a chance to host the World Tunnel Congress. Even that would be taken on for the purpose of organization by the TAI. We conduct Tunneling Asia once in 2 years. It is due this year also. We have to take a call whether we're going to conduct it physically or we'll have to conduct it like anywhere else. We will have to do a virtual conference. In given months to 2 months' time, we will decide. We remain very concerned about the safety aspects of the tunneling, and we can assure our members of the ITA this is one area where we are working. Like always, we have another young group which is, sort of developing its own skills. That is the young members of the what they call Y8AM. Now, their membership is also increasing. All those members who are younger in age profile, less than 35 years of age, have got together. Now, with us, we also have a small little organization called the Center for Excellence for Tunnels at the National Highway Infrastructure Development Corporation Limited, NHIDCL. And this is another platform for the advancement of tunneling development. They provide the thought leadership, the strategic advice, and the problem-solving concepts. Now, I would only request, I believe there has been a very sad news that Mr. Malik, who was heading this small little organization, we have lost him very recently. Our condolences to the organization, to his family. But till the organization finds a suitable substitute, those who are manning the show, please remain free. Feel free to associate with us and collaborate with us. Now, this much about these two organizations. Coming to our speaker for the day. Well, I think by now I have introduced him so many times that I don't even need to refer to my notes. But even you don't need to be refreshed. I think each one of you know him and know him pretty well. But to honor him on this platform, once again, in a very short time, let me reintroduce Dr. Aaron Wagner. Ladies and gentlemen, in the field of tunneling, he is a very, very well-renowned person. As the name suggests, he's a doctorate, a PhD in this subject. He's a licensed master builder. He's a government counselor. He's a chartered expert at court. He's been a consultant with the World Bank for more than 15 years. He's an international consultant for all kinds of underground structures. He has got more than 40 years of experience in the tunnel design and also the construction and consultancy. And needless to say, I mentioned last time also that all this is not complete. To complete the entire picture, he has also been a professor at the Graz University, a world-renowned university in the field of tunneling. At the ITA, he's been a vice president, and he still is an expert member in the executive council of the ITA. He's a real time enthusiast who wants to share his experiences, lifetime experiences. You will see that how much energy he packs into the subject that we give him, and we are wonderful to you, sir. That every time you speak to us, it's a treat to listen to you, and we know that the way you share your experiences, that you have that wealth of knowledge and wealth of experience with you. Now, coming to the subject proper. Subject that he and us we have chosen is the life cycle assessment. Ladies and gentlemen, I think all of you are aware of this. That there is a concept called life cycle concept. In short, some of us call it womb to tomb, and in some cases they also call cradle to grave. Okay, so whatever you call it, it's the moment a project is conceived till the time it lasts its lifetime is called the life cycle concept. Now there are two angles associated. If you take just a concept or not just a project and see the especially the capital cost associated, it might tell you, oh, it's very expensive. But when you go into the analysis as to what are the benefits, what are the collateral benefits that you drive out of that project, you will realize that the benefits are so many, tangible and intangible benefits are so many, that when you equate the cost is in actual is turns out to be much lesser. Okay, so say for example, when you say take a hill sector, you dig a tunnel into the hill. Yes, initial capital investment is going to be large compared to a road. But just imagine a winding road going up the hill, winding road coming down the hill, so many vehicles climbing up, so many vehicles climbing down, fuel expenditure, wear and tear to the vehicle, accidents, and the worst of all is the damage that we do to our environment. And that's why the first thing that he's going to be talking about is the Environment Impact Assessment, EIA. I think it's very, very important. That is one. Secondly, he's going to compare that cost. When you look at the cost exclusively, and when you look at it from the life cycle concept point of view, that it is not really so alarming as it might appear to be. It may be beneficial edge. The third thing is that, okay, how do we assess the service life? How do we arrive at it? Before you give a design of a project, the life is always given that, okay, we want to design this structure for 100 years, 50 years, 75 years, according to the designs are made. So what goes into the life cycle concept is the capital cost for construction and also the maintenance and the running and the operational costs or upgradation costs. Those are also included into the life cycle concept, and you can draw out a comparison. Assessment of the life of a structure itself is a study. Okay, so I'm not going to speak about it. Sustainable development is another mantra these days. Everybody speaks about it. So when professor is going to talk about all these subjects, I am just briefly introducing to you these subjects. So now I will not spend any more time on these brief introductions, and I will not stand in between you and the speaker. Professor Wagner, over to you. Once again, hearty welcome.
Thank you very much, Your Excellency. I very much appreciate your kind words and your competency all the time, in particular in these days, nowadays, when the whole world is in sort of a change. And we know that it is not ending in a short period of time. I think we will all we have to accept that we will be living with this kind of epidemic conditions, and it will make a big change in our professional life also. As we have been using to meet and to have face-to-face meetings, I think in the future we will have less of that, though we are using communication technologies nowadays which have not been available 10 or 20 years ago. But I can tell you that from the point of view of global population development, we can say that infrastructure is the most important and for us, the most convincing factor in the development of the world. If we look into some other countries also, we can see that those countries who have been investing into infrastructure, they have made significant social, economic, and ecologic progress in their countries. And I very much am honored and pleased to work with Tunneling Association of India and with Central Board of Irrigation and Power to work together with you and to make a small contribution to the development and to the education and training sector for civil engineers. So after this introduction, which I'm very grateful for that introduction indeed, I would like to just give you from that 11th virtual session today a reflection of my professional experience. And there are some examples included in the presentation today, which have been very dominant in my professional career. But they are also typical examples of how the development, in which direction the development is going. So let us just jump over the next overview of the slide number 2 of the training program in 2020-2021, where we have the last of these program today with the life cycle assessment, in regard to sustainability and cost. And let me go to the overview, to the table of content of today. After some slides in the preamble of that introduction, the presentation will include subject of acquisition of materials, and from acquisition to operation. It will be covered in the second slideshow. Then I will talk about the modular process of life cycle assessment, and I will then follow up with some remarks on compact city developments and smart city developments. And I will also talk about the comparison, which we all the time, so in many cases, do between above ground and underground projects. Then I will talk about urban road tunnels and highway tunnels, but also I will spend some time on talking about risk assessment and about sustainable and resilient urban developments. Again, looking into underground urban roads and highways and giving some examples. This is not comprehensive, but some examples on the evolution of technology. Then I will talk about some thoughts on urban systems and coming to the conclusion. It is common understanding that underground infrastructure projects are expensive. You know, some people always think everything is too expensive. But underground infrastructure also is considered to be risky and dark. And that makes it easy to shape public opinion through the media if the media take against such projects. You know, in the media philosophy, only bad news are good news. Underground construction contracting, as with other types of construction contracting, It ranges from small and simple to large and complex and big projects. Life cycle assessment costs are different depending on the scope, depending on the work site location, depending on the sources of funding also. The projects will be built either by union employees or in an open shop, and applicable laws will be considered as well as ordinances and countries or region-specific regulations. The contract provisions usually are unique to underground construction practices. However, they have been developed according to the site geology and groundwater conditions at the site, according to site uncertainties and site-specific risks, special project insurance provisions and payment terms corresponding to the risk, which should be shared in a fair way between the owner of the project and the contractor. Now, talking about life cycle analysis to evaluate the environmental impact of a project and the consequences generated throughout the life from different aspects of the project, such as materials acquisition, its construction, its operation and maintenance, and finally its disposal and end-life treatment at the end of the project. Life cycle cost analysis is considered to be an appropriate methodology by decision makers to evaluate the economical and socio-environmental sustainable infrastructure consequences of that project. Life cycle cost analysis has many applications, among which it allows decision makers to compare and to choose the best alternative to achieve sustainable development. Usually, alternatives are considered between above ground and below ground structures. And in that respect, many times we compare bridges and underground tunnel structures. Life cycle cost analysis is also utilizing the incision-making process during the planning and design stage in order to evaluate all constraints related to that specific project. And to meet sustainability goals, it is necessary to evaluate all economic practices and economic activities over the life cycle of a project. Planning at the early stage of the projects may be more cost-effective with a resilient and productive construction over the life cycle with less environmental impact. So that gives an additional dimension to every project if we not only consider the actual cost of construction in terms of excavation, in terms of tonnage of steel and cubic meters of concrete and so on, but to include the life cycle cost of the very project and if there are alternatives between different alternatives. The life cycle assessment, as we know, underground infrastructure may be susceptible to deterioration and issues associated with changing technologies, climate change, and societal needs. So aging of the underground infrastructure is just normal. Underground space development requires a long-term commitment to technological advancements in an environment that is friendly to improved planning, innovation, and implementation. There exist few data regarding the environmental and social impacts and life cycle sustainability of urban development that can inform technology and administrative decisions related to long-term. Long-term means considering decades or even centuries of infrastructure operation, maintenance, and reduced costs. Comprehensive and scientific retrospective studies of the direct and indirect costs and impacts of various types of underground projects are needed to evaluate the usefulness and economic, environmental, and social impacts so that future planning can maximize sustainability. If we do not cover these life cycle aspects and assessment of life cycle costs, the projects nowadays, in particular infrastructure and underground infrastructure projects, are not completely in their consideration. Now the question is, what are criteria for sustainability? Sustainability denotes careful stewarding of available resources, observing ecological, economic, and social criteria over the entire life cycle of a project. From the economic point of view, it is not sufficient to base a design on construction costs only, because we have nowadays the tools and the modular processes of considering life cycle as part of a project. The concept of life cycle cost estimate, which is already used as standard in many other fields also, forms the starting point and is adapted and further developed to suit the specification, in particular of tunnels, as we are talking about tunnel structures essentially. In order to implement a structured and transparent procedure for the determination of life cycle costs, a hierarchic and modular structure of the overall construction works first has to be carried out. So this covers the criteria of sustainability. Now, we are living in times of climate change and also on the influence, in particular, of CO2 concentrations and in particular on the connects between carbon dioxide and global temperature increase. So we are talking about cost versus different options for life cycle project stages. The life cycle project stages in simple terms are the design stage, the construction stage, and the operation and maintenance stage. Whereas at the early life cycle design stage, we are looking into different options. The number of options is maximum at the beginning of the project, while the cost spent on the project at the beginning of the design stage are less. And we have service cost developments at the beginning of the project with regard to the options. So the broad process required to achieve a sustainable tunnel includes the consideration of the full project life cycle from the outset with so-called feedback loops. It's attempting to use the minimum amount of embodied carbon possible and minimizing the amount of future operational carbon emissions. complying with current sustainable initiatives, and representing a holistic, collaborative effort between client, designer, and contractor. So from that point of view, we can see that with the increase of CO2 concentration, we have also a development of increased global temperatures, where the critical temperatures in Fahrenheit are between 57.5 and 58 Fahrenheit degrees. Life cycle, whole life cycle cost, WLC in short, is covering from the externalities to non-constructive costs in comparison with the income, which finally leads to the life cycle cost and to the further distinguishing between construction, operation, maintenance, and end of life costs, with all of these phases covering environmental costs. So one of the most important being the ability to allow a company to reduce costs at the overview of the project. If the project is going over the budget, we have to look at life cycle costs to help determine what alternatives are available to achieve cost reduction. Alternatives such as design, building components, and much more are just examples of such alternatives in life cycle costing in construction. What are the benefits of life cycle costing? First of all, life cycle costs shall help to determine alternatives for a more cost-effective and benefit-based project. So we like to optimize cost efficiency and benefits. Factors that are determining over the entire lifespan of the project should allow the company, the owner, to encompass what they should do entirely. It is important to know that a life cycle cost doesn't necessarily determine the cheapest option from the point of view of starting the project available for a construction team. It actually helps a company to determine the largest economic advantage with consideration of cost and benefit over the life of a project. Besides the ability to reduce costs, a life cycle cost helps a construction team to determine the maximum benefit of that project. This is done by analyzing the cost with the benefits in mind. Combining the two is what determines the overall success rate of the project. Life cycle cost estimate starts with the evaluation of underground structure and often results in disputes regarding their construction cost without considering their long-term benefits and neglecting their life cycle cost. So that can bring a project to a failure state. There are trends towards sustainable structures in underground infrastructures. These has recently increased, and that is one of the benefits of life cycle cost evaluation and estimation. While estimating life cycle costs in civil engineering projects, the respective components reflect this development. The components which are determining the project itself. Unless few publications only deal with calculation of life cycle costs for now, for underground infrastructure. And unfortunately, not enough is published on that. Life cycle costs are poorly published, though they are in general the most costly parts of the infrastructure project if we consider the whole life cycle of a project. We look into life cycle costs from start to end. What are resource extraction, actual resource origin has to be questioned, as in particular regarding cost, environmental impact, important in determination of the resources of the project. After resources, actual construction happens, and the best suited contractor should be awarded the contract from the point of view of cost, reputation, best suited from the point of view of cost and reputation, and in regard to the environmental impact assessment. The third step is the on-site construction, which is the main component of for the company, looking at the area of the entire project. Occupancy and maintenance, the companies have to look into the life cycle cost, which determines everything. Occupancy and maintenance of a project should be just as heavily looked after as everything else. Demolition is a key factor in ending the life cycle of a structure, being the important piece of this process, but it is not yet the final step of the project. The final step of the project is the consideration of recycling, reuse, and disposal. After demolition, it should recycling, reusability, and disposability has to happen. Cost, environmental impact, and process ending concludes the process of life cycle costs. In conclusion, life cycle cost is most important to be analyzed as part of the entire cost and to compare and to contrast alternatives for an economic benefit. From acquisition of material to operation, we have to look into the life cycle cost over the whole project, for instance, for 30 or more years. So the systems acquisition covers about 20 to 40% of the whole, and the operating and support 60 to 80% of the whole life cycle cost. Life cycle assessment has to study the environmental aspect and potential impact throughout the construction of the structure of the life cycle, from raw materials, acquisition through operation, use, and disposal. General categories of environmental impacts need the consideration, including resource as well. Service life and capital cost are on this graph, which considers assets of project identification, strategic planning, and advanced life cycle, advanced feasibility design phase, preliminary phase, the detailed design phase, and the installation, construction, commissioning, and handover of the project. So at the beginning of the project identification, we have approximately 75% of the project cost which is decreasing with the further development of the project to 35, 20, and 18% of capital cost reduction opportunity, while on the other hand, the percentage of decisions affecting the total life costs are increasing. There is a standard in development in ISO 15686 dealing with the service life planning and the decision process addressing the service life, for instance, of a tunnel structure. It shall be ensured a proposed design life in establishing its service life and secure a life cycle cost profile with addressing environmental factors like life cycle assessment. The service life planning is increasingly being linked with the sustainability development and the whole value of the life cycle. The life cycle costing and assessment starts with the initial costing, service life costs, maintenance costs, operating costs, and finally disposal costs. So this is called the whole life cycle costing. It is the process of compiling all costs that the owner or producer of an asset will incur over its lifespan. The costs include the initial investment, future additional investment, and annually recurring costs, minus any salvage value. The concept applies to several decision areas. The return of investment regarding in capital budgeting, total cost of ownership is compiled and then reduced to its present value to determine expected return on investment and net cash flows. So there is a modular process in total of scope of the analysis, followed by the development or adjustment of the life cycle cost model, the definition, the defined team and collecting information, the populate the model, the review and optimize of the model, the decision and implementation of the solution, and finally the maintenance of the model. The modules represent independent units built up for comparability between different alternatives. The process variety is then assigned independent of life cycle phases. The method of structuring enables a recording and evaluation of life cycle cost. The evaluation can be related to a process or a life cycle phase. The modular format permits an evaluation and optimization of different components and elements of the project. The probability-based extension of the model is provided using simulation models, and the modular process model is life cycle cost model, which determines and optimizes the total cost of a tunnel to achieve economic sustainability, which is the final goal. In a short graph, an overview of life cycle cost analysis, we have a lifespan, or so-called estimated life of the project. We have total costs and replacement costs, and then we have costs over time for the refurbishment. of that particular project. The generic cradle-to-grave life cycle covers the mining of the project, the primary and secondary material processing, the fabrication or construction, the reuse or reuse, and the disposal, and finally the landfill, which may be the final ending the life of the project. The life cycle cost of the project is important for the company to analyze a project entire cost and to compare and contrast alternatives for an economic benefit. It's an important tool that a lot of construction companies nowadays have to utilize when they consider the project. What is the life cycle benefit and the life cycle cost? Underground space developments provide the opportunity to use surface space for other purposes such as green space, and I will give you in the following slides an example from the Boston Central Artery and from another project in the western part of America, from the Alaskan Way in Seattle in Washington State. The parks or other above ground development within or closer urban centers use, while quantification of such opportunities is sometimes difficult, but should be included in the consideration of the sustainability of a project. Low impact design of infrastructure systems shall reduce the environmental impact, and transportation costs is now incorporated. Hello. Incorporated into urban development, and this has been focused on the Transport Research Board annual conferences in Washington in 2009. Can you still hear me?
Yes, sir.
Hello. Okay. So let's talk about compact or smart cities. These are trends which support an underground development concept, including a wide range of underground facilities contributing to efficient and high livable environment. The economic benefits of life cycle considerations are derived from utilizing the subsurface as part of the provision of housing, transportation, commercial, industrial, and other utility facilities. In conclusion, it can be said with regard to life cycle benefits that expenditures made during planning, design, and construction phases are relatively small compared to total life cycle costs of that asset. So therefore, they are so important. Now, let us consider compact development and smart cities, and take the example of the Boston Central Artery, where an elevated structure has been compared with an underground structure. And you can see, and I spent many years in traveling from Boston to New Hampshire. You can see on the left side of that slide, Boston with the elevated structure prior to the installation of an underground structure, which has happened during that central artery project on the right side of the slide, you can see the above ground structure and the underground structure below. So the Central Artery Boston project has been one of the major urban projects as an example for the increasing of the population in that urban area, for the change in transportation from individual transportation, from individual traffic to mass transport traffic. So this shows the braced excavation for a cut and cover section of that Boston Central Artery, which during construction, of course, is having a very heavy impact on the surface life. But finally, after completion of the project, the benefit is shared by everybody. The Boston Central Artery also has been focused on reuse of excavation materials. The excavation material from Boston Central Artery, which was also called the so-called Big Dig project, is uncontaminated, has been used to stabilize slopes and fill and cap the landfill to convert it into recreational landscape and recreational use. The material was transported in more than 4,500 barge loads, these are big ship loads, to the island beginning in 1992 and was used up to cap the landfill with a 2-foot clay cap. The cap created an impervious layer that would serve to keep precipitation from mixing with the wastes beneath and leaching into the harbor. The excavated fill was mixed with biosolids from several waste composting facilities in New England to create topsoil that was subsequently vegetated to keep cap in place. Approximately 2,400 trees have been planted and 26,000 shrubs were planted on that fill. In 2006, a 114-acre park opened after 15 years of cleanup activities. The park is operated by the National Park Service and houses a visitor center, several miles of hiking trails, and also a swimming beach. So you may ask why I do know all these details, and I did not include that in the presentation, but I have been involved in Boston for many years for the cleanup of the harbor with a so-called also Big Dig, 15 kilometers into the ocean to deposit sewage from that whole area. So I'm quite familiar with the Boston area for that reason. So let's talk about above ground versus underground projects and impacts. And it has to be mentioned that there is an anecdotal or partial evidence of the positive environmental and financial impact of replacing above ground transportation structures with underground alignments on neighborhoods worldwide. According to an in-depth review of the City of Boston tax assessing records by the Globe, in the 15 years since the Central Artery Tunnel project began, the value of commercial properties along the mile-long strip that this year will become the Rose Kennedy Greenway increased to 2.3 billion, or an increase of up to 79% of value. That's almost double the citywide 41% increase in assessed commercial property values in the same period. When adjusted and aggregated over the entire Central Artery project alignment, the increase in land values could be of the same order of magnitude as the cost of such a difficult and expensive project. So that is my preaching always, that when I'm trying to convince public clients, project owners, that the underground solution is cheaper than the above ground project. One of the main components is the increase of land value, and the other component is the life cycle cost. So with respect to both of that, the Central Artery project is a brilliant example in Boston, showing that through lowering down, through going underground with the transportation infrastructure, transport infrastructure, is not only increasing the land value, but also it's cheaper from the point of view of life cycle cost consideration. So when we talk about planning and assessment, the underground transportation tunnels such as the Boston Central Artery project required rebuilding and relocating existing underground utilities in the right-of-way of the tunnel structure. The building foundation may make a reuse of underground location prohibitively expensive, in the foreground expensive, precluding underground parking, tunnels, or other uses in that location. The underground construction may increase cost and reduce flexibility of options for alternative future uses. But it remains, because most underground facilities, even after their useful life ends, extra costs or difficulty of reusing the space continues nearly indefinitely. So there is a gain there in summary. Comprehensive planning effort would recognize that underground space is a resource that should be used in the best manner possible, rather than letting initial uses preclude later uses. Similar conclusions have been drawn with respect to limiting space debris in orbits around the Earth that may prevent use of those orbits for other purposes. So planning really has a high value and is very important to be considered, and also very important to be brought to the public information. Interesting also that cost for mining and lining, as an example, for a 20-foot tunnel, according to data supplied by the Washington Metropolitan Area Transit Authority between 1969 and 1994, it shows that accumulated knowledge and risk management, investment in research and adoption of better technology and contracting practices over the period resulted in cost reductions for actual tunneling construction. And this graph shows you differences between earth, rock, and mixed excavation drawing. But between 1968 and 1996, there is a decrease, a significant decrease in the tunnel cost per linear foot. This is attributed to, among others, to technology and evolution of technology. Urban road tunnel costs may be very different. If you see here, from ABC to MNO, different cost of urban road tunnels per lane mile. This has been collected by International Tunneling Association Working Group number 13 in 2004. This working group collected data during a study of cost and benefits for underground transportation facilities, where the data on road tunnels from 30 cities have been collected in 19 countries, and they were compiled from responses from coming from questionnaires, and the data were converted to a common basis in terms of 1996 US dollars for the cost per lane mile of railway. So they look to be very different, but they are different, of course, not only because of different countries, but also because of different geologies, for instance. The costs vary because of what is counted in each project cost. The variations observed among countries in constructing a lane kilometer of roadway suggest that it would be worthwhile to investigate the reasons for lower costs in some countries, different reasons. Also, the local geology may have played a significant role. It is not expected to be the only significant reason for the observed variations. Differences in design standards, administrative review processes, public engagement, and streamlining of design and construction process may be increasing important also. In order to understand the reasons for varying costs, it is important that the outcome of projects developed in other countries can be judged according to standards other than high costs, and so that factors contributing to high costs can be identified and improved, and yes, clarified also, answer the question why there are the differences, if there are benefits and the difference in costs. So life cycle assessment has different impacts. Environmental impacts in preparing life cycle assessments shall include as follows. It shall include, of course, resources. For example, that may be one reason. It may also have an impact, a direct impact on nature and landscape through undesirable change in landscape. Change in landscape may also include landscape shaping. It may include also impacts from climate change, air pollution, smog, acid deposition, deterioration of the ozone layers. It may include impact also from polluted soils, solid waste, added toxins, groundwater pollution, surface water impacts, biological, chemical discharges may have impacts, toxic discharges may have impacts also. Impacts from noise, impacts from radiation, electromagnetism, radiation fields, ionization, ionizing radiation. The environmental life cycle assessment shall include environmental impact estimates. And environmental life cycle assessment might be limited to only a few critical categories of impacts, such as emissions of greenhouse gases and conventional pollutants. When talking about the risk assessment, we have to look into interdependencies over the life cycle of underground infrastructure as an important and challenging part of assessment of the risk. Application of such tools may inform decision-making by reducing some of the high levels of uncertainty associated with different kinds of risk, especially when dealing with interactions of complex systems. Assessment assembles existing knowledge of impacts of underground development by recognizing numerous knowledge gaps, especially because past studies took narrower view of benefits and costs than required for life cycle sustainability perspectives. A variation and uncertainty in the performance of underground development may also be part of the risk assessment, especially regarding extreme events such as earthquakes or floods. Advantages and disadvantages for underground facilities necessitate specific evaluations for each type of use and each type of site circumstances. So risk assessment shall include all these applications and advantages and disadvantages. Life cycle costs runs through different phases. And on the graph, you can see these phases starts with planning, then design, then construction, and finally maintenance. And you can see that the level of influence in the planning at the beginning of the project is quite high, and decreasing influence decreases over the time, whereas we have an increase of total cost over the lifetime of a project. So the life cycle of any infrastructure project is grouped in that 4 phases: planning phase, design phase, construction phase, and operational and maintenance phase. Infrastructure maintenance management is important, as the maintenance of any infrastructure typically results in up to 70% of total cost of life cycle of infrastructure assets, as illustrated in the graph on the right side. So it is a very, very imperative, influential of the maintenance. Construction and maintenance of life cycle, the level of influence through each phase of decisions on total life of cost infrastructure asset is very, very influential. The life of the asset, according to the horizontal bar chart, indicates a typical lifetime frame for different phases over the life of infrastructure asset, while the upper part shows plots of increasing cost. That dashed line, I can look back, increasing the total cost, and decreasing influence over the life of the infrastructure asset. During early phases of decision-making, planning, design, and construction, we have comprehensive consequence for expenditures later in the life of that asset. And if we take, for instance, infrastructure from the point of view of railway environment, costs typically vary between 20 and 30% of operating costs, depending on annual capital investment. Again, the operating costs are much, much higher than if we look back, much higher than the maintenance and operation cost of the project. Now let us talk about sustainable and resilient urban development and contributions to underground engineering. An urban setting basically is a system of systems. So they are overlaying systems. And the broadest relationship between underground space use and the essential element for urban sustainability are systems on top of systems. The physical qualities of infrastructure related to transportation, related to shelter, related to food, to water, and key material resources contribute to sustainability or make them vulnerable to hazards as described above. The risk, it focuses on more direct relationships in terms of maintaining enduring, livable communities and enhancing risk mitigation through the use of appropriately planned and designed underground facilities. Advances in human safety issues, analytical technique for life cycle cost assessment of underground facilities, and the broader triple bottom line analysis. Triple bottom line means financial, economic, and social performance, and specific technological advantages associated with enhanced sustainability are discussed under safety aspects and are discussed under sustainability and resilient urban developments. What are the transport system challenges and opportunities? Construction of major underground transportation projects often require significant relocation of in situ underground utilities along public rights of way. Excavation work and relocation needs of the project provide key opportunities for renewing and rationalizing utility provision in an area to provide for easier future maintenance of those systems. Benefits provide, an overall benefit is provided through the urban community using a system of systems of analysis rather than a project by project analysis. So systems to systems analysis is crucial for the final evaluation of an underground transport project. Sustainability of an underground transportation system is improved when system design allow a much more flexible as possible project, taking into account future uses, potential for additional transportation lines, and intermodal connections. The cost, this can increase initial costs, but provide for better long-term sustainability and, as elaborated before, for the long-term life cycle cost inclusion, which makes the project in many cases cheaper than by only considering installation cost. When talking about roads and highways in urban environment, the underground urban road and highway typically traverse deep below a city from portals at each end that tie into existing service road networks. Tunnels avoid building foundations and other in-place services and leave space closer to the surface for future installation, provided, like in the case of the Boston Central Artery, that you go deep enough and not touching existing foundations. Tunnels constructed at depths will be the lowest cost among alternative underground solutions if a life cycle cost analysis is prepared and geologic conditions are respected. Geologic conditions, hydrologic conditions, and of course climatic conditions are important to be considered. Barriers to free-flowing traffic can be bypassed, travel times can be shortened, and carbon emissions can be reduced for the same distances traveled by surface road. So again, I'm a strong promoter to go underground in urban areas. The diversion of traffic from streets allow more pedestrian-friendly environments in the city. Example, Central Artery in Boston. But another example is coming shortly from the Alaskan Way in Seattle. However, decisions to build underground roadways regarding of the benefits are regularly contested, as shown at the example of the Alaskan Way in Seattle, Washington State. Decisions to proceed require a vote of the people and a coming together of the city, of the county, state, and federal representatives to reach a common agreement. This process is often time-consuming and can result in increased project costs. But it is important to communicate every information about not only installation, but also life cycle cost. Now, talking about a second typical example for a successful project, the Alaskan Way viaduct replacement in Washington, in Seattle, city of Seattle. You can see in the picture the Alaskan Way viaduct, which was a double-deck expressway along the city's waterfront. Everybody who has been in that area and has looked at that at the time when there was the Alaskan Way still there will understand that going deeper did make a lot of sense in that case, in particular after they had a terrible earthquake in 1982 or 85, I believe, which basically was the initial start of considering an underground solution. The decision was made to bore an urban underground bypass expressway and remove the damaged viaduct and restore an accessible scenic waterfront. The tunnel finally was a 3.2 kilometer 4-lane bypass roadway tunnel located deep enough under the city to avoid the century-old Burlington Northern Santa Fe Railroad tunnel in daily use, a large interceptor sewer, and existing building foundation. That was a tremendous challenging project at that time. And Seattle now recovers views of Elliott Bay, Puget Sound, and the mountains after removing the viaduct. So let's look into the removed viaduct. This is the aerial view of Seattle waterfront nowadays, and at the time when there was the viaduct and before installing the tunnels. And on the right side, you can see the new concept, which increases the pedestrian access to the waterfront and improves general access to adjacent commercial enterprises. Totally new feeling of the city environment in that particular case. Now, the Alaskan Way Viaduct, after it proposed and after it has been realized, the bored tunnel concept. The alternative solutions did include a new, wider, two-level viaduct on the same alignment. The replacement of the viaduct by a wide surface street carrying significant levels of through traffic. You can see in that concept of the proposed bored tunnel of the State Highway Road number 99. Everything is included in that huge tunnel, which was the biggest tunnel at that time. It was almost 18-meter diameter circular tunnel, precast concrete segmental line tunnel. TBM board. The relocation of the highway on a bridge or tunnel over or under the Elliott Bay, and the alternative, which was also considered, do nothing, intended to limit traffic growth and create a demand for better public transit through continued more disruptive road congestion, which definitely was not realized. And the discussion on the alternatives were studied and publicly sufficiently discussed. So finally, the people of Seattle decided for the bored tunnels, and it was not an easy project for sure, but it was finally a very successful project. So I would like to give you an idea of what underground engineering, tunnel engineering, among others, means. It means, among others, permanent evolution of technology. So the innovation can advance engineering practice, increasing appeal of underground space. Advances of the technology have been crucial to efficient and economical developments. Take a look to the picture on the right side. It shows the crossing of the Thames, River Thames in London by Isaac Brunel in 1860, 1870 with a shield. And you can see that was a tremendous effect. It was, firstly, it was the first shield in the world to use to go under an existing soft ground tunnel under a river of the River Thames. It still exists today. And on the lower part of the picture, you see the evolution in technology with a conditioned and pressurized EPB, earth pressure balance shield machine, where the screw removes conditioned muck and provides the pressure on the face with the linings erected in the tail of the shield, the grouting injected through the tail as the shield is shoved forward, and the chambers which supports the face, preventing inflow of water and soil, So this is a very convincing example of progress of technology. The developments have been motivated by challenges encountered during construction. For instance, the shield technology industry has contributed essentially to or has been even instrumental in many of these evolutions of development. And tunnel boring machines are an example of the industry-led development, as are waterproofing and ground improvement technologies that have been introduced and popularized and have been mentioned in previous virtual lectures also. So technology really has contributed a huge part to the development of infrastructure in our world nowadays. And now we even can talk about projects which have been engineers' dreams, but now they are realized, which would be another virtual lecture in one of the future sessions maybe. So besides or part of the technology evolution is also we have to talk about data management evolution. Monitoring data is continuously fed back into enhanced design and construction. So that means that we are living with the data which we produce immediately and make use in progressing our projects. Advances in construction monitoring are moving away from physical measurements to wireless connected sensor networks. 30, 40 years or more ago, we have had convergency measurements manually done. Nowadays, everything is data management, and also everything is done based on lasers. Data allow contractors to optimize construction and to increase at the same time safety. Integration of data from multiple projects can also facilitate improvement of equipment, improvement of design, improvement of performance, and prediction and understanding of material properties. Monitoring for enhanced safety becomes critical as larger diameter and shallower infrastructure facilities are increasingly proposed, in particular for urban areas. For urban areas, in the respect that global population is increasing not in rural areas, but in urban areas. So urban areas and urban infrastructure investment and improvement are crucial for the development of our culture and our societies. So with data management, we really can do a significant step forward, starting from the engineering design objective regarding economic underground space and minimum impact on existing facilities through further data management in simulation models of anticipated ground deformations, which later will be verified in construction, through engineering design, through further construction activities, now limited records and new with detailed records, then further field data collection from manual non-real time to new sensors and wireless technology, to further data storage and display, which is now simple graphical display lacking construction information with new virtual reality, with updating simulation models of future ground deformations, now ad hoc upgrading and updating and non-systematic, but in the future to new intelligent updating, and further to adjustment of engineering design and construction activities to control deformations, again moving to construction activities. So that's a permanent feedback of data management according to data evolution. Now, talking about urban systems, the development of underground space as part of sustainable urbanization requires coordinated communication with all stakeholders to better incorporate site-specific conditions, to greater flexibility, to long-term community needs into infrastructure system design, and finally to optimize life cycle management. There is relatively little strategic coordination of underground infrastructure development. Hopefully there's more coordination in the future. The administrative support and management of underground infrastructure as part of an integrated, multidimensional, above and below ground system of urban systems is vital to urban sustainability. So administrative improvement is essential and very crucial. To give you an example from the geotechnical point of view, to save Bangkok and to stop Bangkok sinking, there is major infrastructure investment necessary, which should be based on long-term life cycle assessment to be implemented to provide future sustainable urban living conditions. And that not only concerns Bangkok, that concerns most of the mega cities nowadays are coastal mega cities, like Jakarta, like Shanghai, like New York, like Rio de Janeiro or Buenos Aires. So most of the megacities of our world nowadays are having problems with sea rise level in the context of climate change and polar ice melting and so on. So sea level rise associated with climate change poses significant risk to underground infrastructure, which has to be considered also from the point of view of risk, but also from the point of view of opportunity, because underground infrastructure can provide more safety, can provide a significant safety contribution to urban cities in coastal areas. Talking about development and sustainability coordination could lead to better management of research investment, of optimized decision-making, of reduced risk for federal development projects, and for better leveraging with state and local entities. Also, planning by local governments of city growth does occur. There is little analogous control of underground space, and even less control that coordinates above and below ground development. So the recommendation is make more coordination between above and below ground. The market forces encourage workforce, capacity growth, and urban infrastructure development in an ad hoc manner inconsistent with urban sustainability. So if we look to the graph, then we can see the comparison, or we can see the relation between urban space with increased concentration of development activities due to urbanization and climate change with respect to increased temperature, heat island effects, sea level rise, increased precipitation, which leads to natural disaster, urban floods, which also has to be followed up by urban disaster prevention. As vulnerability increase and discriminate land use, lowland development, concentration of population and industry, all this is indicating its vulnerability, whereas the risk has to be assessed with regard to urban disaster prevention and facilities installation for direct damage facilities, secondary direct damage facilities, and secondary damage facilities as well. So we need system management, infrastructure development, operation and management, which requires management of complex physical, social, and environmental systems. So everything is interacting. The development of underground infrastructure suffers from lack of a mission agency or organization dedicated to coordinating development activities. There are, from the point of view of international organizations, starting developments and starting new platforms. The project and research funding tend to focus on solving particular problems with little consideration of long-term impacts on the total urban system. So that is another initiative also by the United Nations to increase this type of platforms. Complex ownership models confuse responsibility for routine inspections, maintenance, repairs, guidelines, budgets, and liability. As we are increasing our population, I think we also have to increase communication between different platforms in order to avoid confusing responsibilities. There is a need to understand the ownership and control models of underground space and to develop guidelines for funding and performing essential periodic inspections, maintenance and repair of individual infrastructure elements. So we are on the road to follow up of all this. Talking about system complexity, we have to talk about the lack of funding, which continues and which would allow investment in equipment and faculty, resulted in substantial reduction in research programs. So research programs are very, very important to continue and should be also animated to investment. The number of university programs dedicated to integrated underground engineering, research, and education are affected. So I know that different universities have different initiatives, and in that aspect, I would also like to mention International Tunneling Association Committee on Education and Training, which is supporting all of these academic efforts, strongly supporting all these efforts to invest and to increase academic programs. There is a critical shortage in education, training, and research opportunities for engineers who wish to learn and practice underground engineering on a global scale. And Central Board of Irrigation and Power and Tunneling Association of India are a very, very brilliant, excellent example of fighting for more education and making efforts to improve and to offer opportunities to all engineers with interest in underground structures. There is a complexity of urban infrastructure systems associated with system design, increase with various demands on above and below ground infrastructure. So this still, I think, is something which deserves to do more efforts and to do more to increase research and to increase projects and programs to compare above and below ground and to show on advantages of the underground versus above ground. Engineers and urban planners could better improve whole life cycle facility performance and sustainability with documented risk-informed approaches. So I started almost a year ago with talking about risk in underground construction, and we are ending up today also with regard to underlining the importance of risk assessment, of life cycle cost assessment, and of the combination of all that. Planning and design that balance life cycle projects needs in terms of service delivery, initial cost, resilience, and effective maintenance of operations. So planning and design is in fact a very important factor. In conclusion, I think we have to say that underground space is a valuable but decisively non-renewable resource. So if you look to that picture here, it's a picture which I think it was developed by the United Nations some times ago, which shows all of the different types of underground structures possible in an urban environment. So we have to think that, I used to say that underground space is limitless. There are no limits for underground space, but for sure it is non-renewable. We cannot not renew. We can make use, but we cannot renew. Underground space can enhance urban sustainability only if the underground is thoroughly understood. So we have to understand what is soft ground, what is hard rock, what is mixed phase. We have to understand hydrogeology. We have to understand how it affects, how technology has improved, but still, what do we need to make use of that huge improvements in technology? So underground use and reuse and the protection of the natural and built environments are to be long incorporated into long-term total urban infrastructure life cycle assessment planning. So what I would like to say is that we have to think comprehensively, we have to think holistically about the underground. But there is also something to be said that there is no substitute for experience. So always we should make use of the available experience, and there has never been as much experience as there is experience available today. Thank you so far from paying attention to this lecture today, and I'm very happy to take any question or any discussions after that presentation. Thank you very much.
Thank you, Dr. Haral. Thank you so much. Thank you to all the participants. May we proceed further for the question and answer session? May I request to the participants for their questions?
I would also like to mention that any question can be submitted in writing, and as I have done before, I will give you a response in writing also. So if you like to take more time to think about what has been presented today, just take your time.
Okay, no questions. Fine. Ladies and gentlemen, I'm sure you have questions, but then probably you will like to write in private to the professor. You can do that. He's already told you that you can write individually to him. He will respond. So thank you, Dr. Wagner, for another, I would say, a very, very comprehensive rundown on the important subject of the life cycle concept, making the whole thing so simple, appear so simple for all of us to understand. A few takeaways, if I can summarize on behalf of all the attendees here. Firstly, there is no doubt that underground space is the future. We cannot go vertically beyond a certain limit. We have to go underground, especially to create facilities. And like you said, there is always a finite limit to going underground also. You cannot just dig anywhere. So there comes a dilemma now. There is a predicament, at least in my mind, which I'm going to discuss with you separately. That look, the overground structures and which are existing now, and the future underground structures will have to coexist. So if they have to exist at the same time, we do not want any conflict between the two. So if you do not want any conflict between the two, are our engineers and the urban planners sitting together to think on these lines? Well, my simple answer is no. And I'm not talking about in India. Elsewhere also, I have not seen urban planners being brought on the scene much. Therefore, my cue from here is, and through you, and I will also highlight to our ITA, that in future, one of the conferences less dedicated to urban planning, where it is dedicated to coexistence of overground and underground structures.
Yes.
Professor, are you in agreement?
I'm totally in agreement with you. Yes, very, very, very precise.
If you recall, just for everybody's information, when we were in Naples, the theme of the conference was archaeology, architecture, and art.
Yes.
Okay, now from underground space, we had gone to archaeology, we had gone to art, and we had even gone to the other things, the architecture. So never before that we spoke about the architecture, never before that we spoke about the art, and never before that we spoke about the archaeology concerning the underground space. This became all time important. So therefore, I think one session, I will write to Oliver and the president today itself, that maybe 2 years, 3 years, or once the themes are decided, let's dedicate one particular theme to the coexistence of overground and underground structures. And we will invite a lot of urban planners also. I have rarely seen urban planners as part of the IT. Okay, that is on the sidelines. So therefore, you have brought out, and I think all of us understand that there is no doubt in our mind that underground space, utilization of the underground space is the future. And underground space is a complex subject, and it is driven by the systems rather. So if it is going to be system driven, okay, then we have to devote time, energy, and resources to those systems. Who's going to own those systems? Who's going to run those systems? Who's going to maintain those systems? And who's going to design those systems? And I agree with you that more research needs to be done in this field, and more agencies need to come forward with funds where more and more focus can be given to this part of the study. And since I'm also associated with the CBRE, that is our Central Building Research Institute in India, I'm one of the research council members. I think I will also share this with the directors, that why don't you dedicate every year at least 1 or 2 research projects in this field, that is the system integration for the underground space, which is a gray area. So these are things that you mentioned. You also brought out 2 very important aspects, that the whole thing has to be, this life cycle concept has to be thought out during the planning and design stage itself. And it must take into the resilience and effective operation and maintenance. And when I say resilience, I am now saying resilient more to the climatic changes and other risks. You build up the infrastructure, just see what is happening in Kerala today. Just see in India, I'm talking about, there is a cyclone there. You see even in Gujarat. So you make roads which are not climatically resilient, they get washed away. First flood and they're gone. So we have to now start looking at these risks, climatic risks that we are facing, and all our infrastructure has to be resilient to cater to the developing threat, developing risk of the climate change. That is one. Second is that you mentioned about the sustainability. I agree with you that every infrastructure that we now create, more so in the urban setting, it has to be sustainable. We cannot do something and then after 5 years, we dig it up again. It's very, I'm sorry to share, but then it's a fact on ground that it's very common to see, at least in India, that on one side you find that a road has been beautifully done up, and the next day you find that the sides of the road have been dug up because somebody forgot to do the drains. So when we create infrastructure, we have to not only create it resilient, we also have to see from sustain. It should sustain itself at least for 2, 3, 4, maybe 5 decades. Otherwise, we will keep investing and reinvesting and keep wasting our useful resources. So I have nothing more to say. Thank you once again, Professor. It's always a pleasure listening to you, keying into your brilliant ideas and sharing your experiences with us. Thank you once again. I take this opportunity on behalf of everybody present here to wish you a very, very happy and very safe times ahead till we meet again. Thank you. Thank you, everyone.
Thank you very much for your very kind and very competent words. And I only can say, I could not more agree with you than what you said and what you precisely have crystallized from these roughly 1.5 hours of virtual session. It is just let me call it a harmonized interest, which I feel from your side with the ideas which I presented from my side. It is just fantastic. It is really excellent, and I can only say I would be more than honored and more than pleased if I can further provide support and assistance and contribute with my experience to the Tunneling Association of India and to its representatives in the board of directors and to the people of the members, as you mentioned, more than 600 members of the Tunneling Association of India. That's a huge community of engineers and people who are interested to move further in underground infrastructure implementation. So I really would like to thank you for the opportunity to be with you and to have discussions with you. And I look forward to have further contacts with you. Thank you very much from deep.
We will get
heart.
Thank you. Okay, thank you very much. We can de-link now. God bless you all. Bye-bye.
Thank you.
Thank you very
all.
much.
Thank you.